And this is, darn it, 11, 17, 14. So someone had asked when you looked at your periodic background video, somebody had said, well, what about hydrogen? Is it classified as anything? And it is. Hydrogen is a non-gas. Now, there's just one little problem with that. Or it's a non-metal, rather. The non-metals are all supposed to be over on this side of the periodic table, right? Yeah. That's where the non-metals are, and that's your carbons and your oxygens and your nitrogens. Great. But hydrogen is clearly a non-metal behaviorally. It behaves like a non-metal. What's hydrogen's electron configuration? Yeah, it's 1s1. That's hydrogen right there. Well, that puts it in what group? It puts it in the S block, and it puts it in group 1 specifically. But those are metals. So if we put it in there based on electron configuration, then hydrogen goes here, which is where it's typically shown. If we put it someplace based on how it behaves, it would be over in group 17. And that's why it shows up in 2 places on the periodic table you've got. So we treat it as a group 1 element, but we know that it doesn't behave like a group 1 element. Now, helium is the other weirdo. And helium is in group 18. It's a noble gas. It behaves like a normal gas. Where's its electron configuration put it? What is helium's electron configuration? Yeah, 1s2. Well, that would be a group 2 element. But it behaves like a noble gas. It is a noble gas. So the reason, so think this through. What makes noble gases noble gases? Well, unreactive, but dig deeper. Why are they unreactive? No. Full shells. And it's typically full S and P. So they've got an S2P6 configuration. Well, helium's only operating on the first energy level. It's got a full shell. It just doesn't have any P's because the first energy level doesn't have any P's. So that's why it behaves like a noble gas. We treat it as a noble gas. But if we looked at electron configuration, we would predict it was in group 2. It's not a group 2 kind of element. It's just not. So we put it in group 18. Now, what's so special about H and E other than the fact that they're weirdos? They're originals. These are the elements out of which everything else got smashed together and made. So where do we produce helium in the universe? The sun. Comes up every morning. Yeah, one answer comes up every morning. Take a bunch of hydrogen, smash it together at high velocity and high temperature, you get a bunch of helium. That's fusion. And these two are the first atoms that would have existed in our universe, and then they got compressed and fused into everything else. So they're special cases, and they behave a little bit differently. Okay, so we're going to start to talk a little bit about the S block elements, and these are groups 1 and 2. They're metals, and they are incredibly reactive. Now, when you think of metal, what you probably think of is what's actually a transition metal, the D block. You think of things that are shiny and lustrous and very hard, and you can build buildings out of them. You can't build buildings out of group 1 and 2 metals. That's not the kind of metals we're talking about here. Actually, most of them, if you had them isolated, they're pretty soft materials. I mean, you can cut a chunk of sodium with a butter knife. And I'll show you a video of that in a little bit. You don't find chunks of sodium laying around. They are incredibly reactive. They're like that, whiny, needy friend of yours who can't ever be alone. That's sodium. Can't ever be alone. Constantly needs to be in contact with somebody else. So we have lots of compounds formed from group 1 and 2 elements. This is really important, that the number of electrons in the highest occupied energy level is equal to the group number. What's another word for number of electrons in the highest occupied main energy level? You learned this in physical science. It starts with a V. Valence. Yeah. So the valence electrons, valence E, for group 1 and 2, it's the same as the highest occupied energy level. I'm sorry, same as the group number. Same as the group number. And these groups have their own names, alkali metals and alkali earth metals. I'm less concerned that you know that than that you know how they behave in general. When we start talking about forming compounds and forming ions, this becomes really important, that you know immediately right off the top of your head how many valence electrons something has, and then you're going to know right off the top of your head what kind of ion it's going to form. Okay, so the next one we're going to talk about is the P block. And we talk about the P block next. We don't go straight to the D block because, of course, P is the next shape of subshell that we deal with. We go from S to P. So this is groups 13 through 18, and you've got your color-coded periodic table out, I'm sure. That's these guys. When we talk about these with the S block, those are called main group elements. Okay, so when somebody talks about the main group elements, they're talking about something that's in S or P. Main group does not include D or F. Here, the number of electrons in the highest occupied energy level, in other words, they're what? In other words, they're valence electrons, is equal to their group number minus 10. Okay? So if you are in group 13, how many valence electrons do you have? 3. If you're in group 17, how many valence electrons do you have? 7. The flip side of that is I will ask you things like, if something has 5 valence electrons, what group is it in? 15. But you have to be able to do that when I'm not telling you, hey, it's in the P block. So, you know. Okay. 18 has got that full shell, that full subshell, 2 full subshells on the uppermost energy level, and that's why they're so stable. And you already know this from physical science, I'm pretty sure. We'll talk a lot more about it. Everybody wants to be like the noble gases. That is the most stable configuration for any atom. And remember that the universe is incredibly lazy. Being unstable, you're fighting against the forces of instability. It takes energy. Everything is seeking stability. It's seeking nice, low energy, stable conditions. You know, we very often use language and I've heard this criticized very specifically. So I'm shifting it. I'm shifting it up. All through, if you did any kind of chemistry, like baby chem in middle school, and all through physical science, you talk about everything, you know, like fluorine wants to be like a noble gas. Well, fluorine doesn't want anything. It doesn't have a central nervous system. It's a single atom. It's a bunch of protons, neutrons, and electrons. It's a bunch of smaller subatomic particles. It doesn't want anything. You want a bowl of popcorn. Fluorine wants nothing. We use that language to describe what pieces of the physical universe are seeking. And really it's about stability. So I do still use that terminology sometimes, this element wants to be, well, yes and no, but I just want to explicitly state and make sure that you're clear. Sodium doesn't want anything. It can't. It's an inanimate cell. Okay, we talked about specific characteristics in the S block, and we said, S block elements are all very reactive, We can't make any statements like that about the P block. There's too much variety. It varies too much. So from one end of the P block to the other end of the P block, you've got all kinds of changes. And you have a combination of things that are metals in the P block. You have all the non-metals are in the P block. And the noble gases are in the P block. So this is a lot of variety. This is a very, very diverse group of elements. We will talk about how things change across that group, but we can't talk about specific characteristics within the group. We'll talk a little bit more in detail about the P block. This is where all the nonmetals exist except for our friend hydrogen, which is classed as an S-block element, even though it doesn't act like it. All the metalloids are here. See what I mean about this being diverse? And we still have a few metals stuck in there. So the big important thing to know about the P block is that this is where the halogens are. And we will use this term, halogens, a lot. This is group 17. Halogens are nonmetals, and they are incredibly reactive. If you go on to a degree in biology or in pharmacy or in anything where you have to take a year of organic chemistry, chlorination and bromination reactions are something that you will know backwards, forwards, inside out, and upside down with organic compounds. Chlorine and bromine are very, very, very reactive, and they tend to react well with biological molecules and organic chemicals that are found in humans. What do we use to kill germs on surfaces very often? Chlorine, bleach. That's because those chemicals are very active. They are reactive and hence active, and they are readily picked up and do stuff with living things and the chemicals in them. So iodine and fluorine are the other ones. Again, we don't find these things alone in nature, as in we don't ever find a single chlorine atom. They're just too reactive, so we don't find single chlorine atoms. Now, we do find free chlorine, but it's not in that form. And we'll talk more about that as we go. But the halogens, the group 17s, are really important to be aware of, and they're a P block thing. Okay, so the D block, this is 3 through 12. This is that middle portion of the periodic table in the standard short form version, that sunken portion. These are also called transition metals. And this is where we start to have the overlaps with the filling the Ds. We get some strange patterns. And if you would be so kind as to, for me, write, and you can do this in noble gas notation, write the electron configuration for manganese and iron. So we already know that in the D block, once we start filling Ds, we have these sort of laggardy things where we're filling a D on the last floor, the last main energy level, the last shell. Something that happens that we won't talk about a lot in this chapter, but you should be aware of, because these are pretty close in energy, and you'll see this if you look in your book. Sometimes some of these S electrons actually migrate up into the Ds. It's something that we don't talk about a whole lot in this chapter, but we do start to talk about in the next chapter when we start doing ions and stuff. It's one of the reasons that a lot of these metals form multiple ions, because these electrons aren't as tightly wedded to where they are as a lot of electrons. They tend to wander a little bit. We call it delocalization. They delocalize. They give up their local area and they kind of drift. So that's one of the other things we see in the D block. For the D block, the group number is actually the sum of the S and D. So the highest main energy level, S, and then whatever D you're filling in. So based on that, what group would you say manganese is in? Group 7. Or, I'm sorry, group number, yeah, it is group 7. Duh. 3, 4, 5, 6, 7. Iron, group 8. I forget when I look at this and I go, wait a minute, no! But the F block doesn't get group numbers. They're just without group numbers. They're groupless elements. Okay, so that's pretty easy. Now, even though those Ds are not highest main energy level, they behave like valence electrons. Okay? They behave like valence electrons, and that's the reason for a lot of those metals, we get multiple different ions formed. There are things that can form a +2 or a +3 or a +4. Huh? You'll get a chart, don't worry. So more about the transition metals. This is the D block. These are what you all thought of when I said metals, basically. These are the things that are what we think of as metals, even though they're not by far the only metals. This is what we think of. All the things you know about metals. They're good conductors, they're shiny, they're hard, they're malleable, they're ductile. That's all true of these things. These are not nearly as reactive as the S block elements, the group 1 and 2 elements. We have some that are very, very non-reactive, like gold. Gold doesn't really form compounds, and that's why gold was used in fillings in the mouth for a long time, because it's unreactive enough that it's not going to react with other chemicals. There are a lot of chemicals present in your body. A woman I worked with years ago, her father had basically the aorta going in, the large artery going into the heart, had the wall had gotten weak and it was bulging out, and that can kill you pretty fast. It's called an aortal aneurysm, and if that pops, typically the survival time is somewhere on the order of seconds, because all your blood just pumps right out into your body cavity and you die. It's really fast in terms of a way to go. So to correct that, they basically put a little mesh sleeve inside the aorta so that there's no pressure on that bubble, and the little sleeve they use is made of gold. And I remember this clearly because she used to joke that her father really now had a heart of gold. You know, it's that unreactive. And titanium is another one that's typically used, like implants for bone. If you've ever, and I think now they're probably actually using resins and probably polymers and kind of plasticky things. But for many, many years, titanium, palladium were used. Like I know somebody who had his leg crushed, industrial accident, press came down, completely crushed the bone. Like there was no bone left, knee to ankle. And there was a steel rod inserted. And that was I think that was probably titanium. But if you know somebody who's had pins or plates, those are typically some of these non-reactive metals. Now they still set off metal detectors at the airport, but they are not reactive, and they are so unreactive you can use them inside the body, and they're not going to be attacked by other chemicals in the body. They're not going to form weird compounds that drift off through the body. That's really important. Okay, the F blocks. These are the things that are working on 4F and 5F orbitals. There are no elements known right now that no elements known right now that have enough electrons to go beyond a 5F orbital. So, you know, when you draw that orbital filling diagram, it kind of gives a fresh look at why we don't draw like 6F, 7F. We don't need to. You know, we don't know of anything that's got that many electrons. Now, the universe is large. I said, you know, what I gave you here is everything in the known universe, which may or may not be true. You know, we don't know if there are scientists working 14.5 billion light years away, which is the edge of the observable universe, who have more elements than we do, that they're aware of. We can presume, because in science we presume, one of the fundamental assertions and assumptions is that the rules work the same way every place, and that the same basic framework and behavior is applicable every place. You know, we can assume that if somewhere on the other side of the universe people have more elements than we do, they're behaving according to the same rules. There's a video, I don't know if I'll have time to show it or not, called Island of Stability, and it talks about the search for the big, big, big elements. One of the things that happens, and we will talk a lot more about repulsive forces, if you put a whole bunch of protons and neutrons together, there's this wonderful thing called nuclear force, and it holds them together, even when protons ought to be repelling one another. But when you get about so big, and you get so many protons in one room, you can't overcome that repulsion anymore. And these things get very, very, very unstable. And those big, giant nuclei tend to just sort of split apart spontaneously. And that's called nuclear radiation. That's all nuclear radiation is atomic nuclei that are spontaneously splitting apart. Okay? When we get into the lanthanides and actinides, many, many, many of the lanthanides and all of the actinides are big enough that those nuclei are unstable. They've got big enough nucleuses that they just can't really hold it together anymore. And so they tend to spontaneously decay. That's, in this periodic table, which has got blanks, this is the 1997 version, the long form. Notice that there are elements that are represented, they're not named yet, with blanks in between. And sometimes it has seemed to nuclear particle physicists that there are actually like leapfrog steps where 118 is more stable than 117. Why would that be? It's bigger. Well, we don't know. 114 is more stable than 113. Huh. So, could somebody on the other side of the universe have come up with element 207? Yeah, maybe. We don't know. There's a lot we don't know. That's a good thing. But back to the F block. So lanthanides, some of them are radioactive. They're all pretty darn reactive. They're about as reactive as group 1 elements. The actinides, however, that very bottom row, those are all completely reactive. Those are all radioactive. Not a single one of them is stable. That means they're all breaking down spontaneously. Atomic radii. So you know what a radius of a circle is. From the center point out to the edge. Great. We actually talk a lot about the radius of atoms. This is atomic radii. And when we measure atomic radii, it is 1/2 of the distance between the nuclei of two identical atoms that are bound together. So there are two identical atoms bound together. There's the whole distance between the two nuclei. Half of that is what we would call the radius. Okay? Half of that is the radius. It's very important to understand that we can only measure this in bound atoms and that they have to be identical. That will become much clearer to you as we go. But that's really important, that it's half that distance, and it is only when they're bound that we can measure them. So go ahead and draw me a Bohr model representation of lithium and sodium. And we have our little protons in there. I'm going to draw it too. Lithium has 3 electrons. 1, 2, 3. This is lithium. This will be my sodium. Okay, so I've got lithium, I've got sodium. Now what I'm going to tell you is that as we go down the group, we said that atomic radii decrease. Okay, so to back up to any discomfort with how this is drawn. Lithium has 3 electrons. The first ring, now remember, we're looking at a Bohr model, and you've been thinking in terms of the quantum model for a long time now. So this is more of a physical science approach. First energy level has just got an s orbital. That can only hold 2 electrons. So we've got our 1s2 is full, and then it starts filling on 2s1. So that's that last electron. Okay, for sodium, we've got 1s2. Let's write it out. 1s2, 2s2, 2p6, 3s1. This one is 1s2, 2s1. So for sodium, we've got the first man energy level has got 2 electrons. That's this. The second energy level has 8. That's that. And then the third energy level has got 1. Is that better? Okay? Good. Good. No, I'm glad we backed that up. So, lithium's got 3 electrons, and those 3 electrons are exerting a force, or I'm sorry, 3 protons. Those 3 protons are exerting an attractive force on how many electrons? 3. It's an even game of tug of war. Now, this little electron out here has got these two, again, to use very human metaphors, these 2 big brothers in between the nucleus and it to kind of protect it from all of the pull. But those 2 big brothers aren't that many. It doesn't have a whole lot of electrons between it and the nucleus. Okay? Now, if we go over to sodium, we have 11 protons. I wrote the number 11 in there, but it's really hard to see. And those 11 protons are exerting a force on how many electrons? 11. And this electron, which is the valence electron, the highest main occupied energy level electron, has got not only these 2 big brothers between the nucleus and it, it's then got a ring of 8 more. Hey, you want to pull on me? You got to go through 10 of them. Huh. I see a cartoon coming from some of my resident chem cartoonists, possibly. So this electron isn't pulled in as strongly because it's got more levels of other electrons between the nucleus and it. What do you think that might cause? Okay. Do you think it'll cause any kind of change in radius? Okay. As we go down the group, forget about the big brothers for a second. We have more protons pulling on more electrons. So in general, just more attractive force. The big brothers are going to come in on the next example. More attractive force in general. If you've got more attractive force, what's going to happen to the radius of this atom? It's going to decrease. Because you've got more protons pulling on more electrons. More protons pulling on more electrons, more overall attractive force, it shrinks in a little bit. Let's do the next example down.